Let's look at a negatively charged electroscope, gold-leaf electroscope. As you can see, it is definitely charged. Now we'll switch on one of these lights. We'll switch first of all the normal white light. Let's see if anything happens. As you can see, nothing. Let's switch it off. Now we'll switch off on the UV, and you can definitely see immediately it discharges. How can we explain this? White light did not work, UV light did. All what happened, we had replaced the zinc plate with, let's say, copper. Will it still work? Here we have a photocell connected to an ammeter, and we have a flashlight at a certain distance. What do you think will happen if we move the light closer? So as I move the light closer, we seem to be getting a fairly small current. And if I move it even closer, the current increases. I can apply a potential difference across the cell so that all the electrons released from the cathode are connected. So let's do that. So I'm going to apply a voltage of about 90 volts. There we go. Let's have a look at now what we have. So as before, we have our photocell, and now the current has jumped up to about 9 microamperes. As I move the source away, it decreases. As I move the source closer, it increases. How can we explain this? Here we have a simple setup involving LEDs, which we can use to work out the value of Planck's constant. So what we have is a number of LEDs that we can independently select. So I have now selected the one that says 570 nanometers. And I basically need to find out the potential difference at which the LED just comes on. What are the experimental challenges in this experiment? So as I increase the potential, you can see there the voltmeter, as I increase the potential, at some point the LED will come on. Now let's look at this carefully. Remember, we're looking at the one which says 570 nanometers. There you can see it's on, but surely it was on before. I just need the potential as soon as it switches on. So how can I improve this experiment? One improvement is to add, like you apply that. Let's have a look. Looking down makes it clear when the LED is on. So in fact, I just want it on, so I'm decreasing the potential until it just switches on. Now, it is a matter of judgment. This is a lot more accurate than without the tube there. So it's still on, still on, still on. I'll judge that as off, and I'll judge that as on. There you go. And I can claim then that the potential was 1.140 volts. Is there a better way? Perhaps I can employ a very accurate ammeter. So instead of looking at whether the LED emits its on, so we can see the light, I can have a look at my microammeter, and as soon as I have current recorded, I can claim the LED is on. What is the key equation that relates to this practical? How can we use a graphical method to analyze the data? Why is it better to use a graphical method? Let's look at how many LEDs we have here. We have 1, 2, 3, 4, 5, 6, 7, 8. So that should produce sufficient data points for us to plot a graph from which we can find H. Can you foresee a problem with some of the wavelengths that we have here? For example, 940 nanometers. Is that visible? Is that within the range of visible light? So perhaps an alteration to the method will be required. Light has a dual nature. It can behave as a particle or as a wave, and we have seen those experiments. How about matter? Can a particle like an electron show this dual nature? What is a key property of all waves? So here we have a setup with an electron gun, maybe able to see it shining through. It's in an evacuated tube. In front, there's a phosphorus screen, so when the electrons hit it, we'll be able to see them. Well, we'll see the end result. And here I have an EHT, and I'm going to start increasing the potential so I can drive the electrons from the electron gun to the screen, and in between, there's a diffraction grating. The diffraction grating at this time is just a very thin slice of graphite. So let's start increasing the potential, and let's see what happens. So it's coming on, and we see that we get, let's increase the potential a bit more. We're getting rings. So let me move closer, let's see if we can see those rings. There they are. So clearly we have a diffraction pattern. What does that tell you about the behavior of electrons as they went through the graphite? What parts of this experiment show the particle nature of electrons? What parts show the wave nature of electrons? What would happen if I increase the potential? So the potential was at 2.63 kilovolts, and I'm going to start increasing it. Look carefully at the rings. And if I then go the other way, so I'm now decreasing the potential, what happens to the rings? How can we explain this? What was the Broglie's hypothesis about electrons that we can use to explain this? There you go, beautiful rings, increasing the potential, decreasing the potential, and decreasing it further, increasing. There we go. If you had to do this experiment and you had to measure the radius of each ring, what equipment would you use? Is a ruler appropriate? What technique can you use to minimize the uncertainty in your measured value? Reduce the effect of random errors, for example.